So this is my first lecture. It will be basically an introduction to probability theory, but through various examples, which are of interest in their own. The first thing which we will do is the birthday problem. So suppose in a class there are 40 students and assume they are all born in 2002, and also assume that they all come from different families so that there are no twins. The first question is, what is the probability that there are two students who are born on the same day? Intuitively, the probability should be very small. Let us do some calculations to find out how small it is. Anyway, the birthday problem is attributed to the 19th century Austrian mathematician Richard von Mises. First, let us generalize the problem. Suppose the class has n students. Labeling them in an increasing order according to their roll numbers, we see that the first student could have been born in any of the 365 days of the year. The second also could have been born on any of the 365 days in the year. So the total choices for the birthdays of these two students is 365 times 365. Similarly, the total choices for the birthdays of the first three students is 365 cubed. In general, for n students, the total choices for the birthdays is 365 to the power n. Now, for all n students to have different birthdays, we must have that the first student could have been born in any of the 365 days. The second one could have been born in any of the remaining 364 days because one of them has already been taken up by the first students. So the total choices for the birthdays of these two students, so that they do not coincide, is 365 multiplied by 364. Similarly, for the first three students, it is 365 multiplied by 364 multiplied by 363. In general, for n students, the choices for the birthdays is exactly this quantity, 365 multiplied by 364 multiplied by ... 365 minus n plus 1. So the probability that no two birthdays coincide among the n students is the total number of possible choices where they do not coincide divided by the total number of choices. So it is 365 into 364 into etc., the number which we just calculated on the previous slide, divided by 365 to the n, which is the total number of choices of all the birthdays of the n students. For n equal to 23, we have that P of 23. This P, the probability that the 23 students have birthdays, none of which coincide, is 0.497. In other words, in a class of 23 students, there are at least two students with the same birthday, is exactly 0.503, which is 1 minus 0.497. Thus, in a class of 23 students, the chances that there are two students whose birthdays coincide is more than 50%. And this result, I find, is quite non-intuitive, but the calculations are completely correct, and so there is nothing hanky-panky about this. This just shows that in a class of 23 students, there will be at least two students with the same birthday. Okay. So let us now just see. This is a data taken from Wikipedia. So when n equal to 1, there's only one student in the class. Of course, there are no two birthdays because there's only one student. When there are 5 students, the same calculation, which would be 365 multiplied by 364, etc., 365 minus 5 plus 1. In other words, 361 So 365 up to 361 divided by 365 to the power 5, that would turn out to be 2.7 0.027. So it's 2.7%. Similarly, for 10, you'll see that the chances is 11.7%, etc. And it's 23. That's exactly what we told you. The probability was 0.507, or in other words, 50.7% is the chances of two students having the same birthday. And if the class sizes increase, then you'll see how it increases. When it's 30, it becomes nearly 70%. For 40, it is 89%. For 60, it's nearly 100%, 99.4%. So and that also you would believe that if there are 60 people in the class, the chances are very high that two people have the same birthday. And there are others given here. Of course, if there are more than 366 students, because there are only 365 days in the year, by Dirichlet's pigeonhole principle, we must have two students with the same birthday. Okay. So let's move on to another problem. This is called the Buffon's needle problem. Consider a ruled sheet of paper where the distance between two consecutive lines is 1 unit. So this could be 1 centimeter or 1 inch, depending on what your unit is. So the distance between any of these horizontal lines any pair is exactly of unit length 1. Okay. And this, by the way, is attributed to the French mathematician, naturalist, botanist, etc., Georges-Louis Leclerc, who was also the Count of Buffon, or Comte de Buffon. Okay. So we have a ruled sheet of paper with these lines marked, which are at a distance 1. And now we drop a needle on this ruled sheet of paper, and the length of the needle is some L, which is strictly between 0 and 1. So it is smaller than 1. Okay. So what can be the positions of the needle? The needle can either intersect one line, or it can be between two lines. However, because the length of the needle is strictly less than 1, it can never intersect two lines, because the distance between any two horizontal lines is 1. Okay. So these are the possibilities, that the needle falls strictly in between two lines, so it doesn't intersect any line, or the needle intersects one line. Okay. These are because we have dropped it at random, we do not know what will happen. So let us now try and find the probability that it intersects a line. And we'll find a very interesting result from here. Let me just say it in advance. We'll actually be able to give an estimate of the value pi. So let x be the distance of the center of the needle from the line. So this length is x. So this is the center of the needle. This length is x. And theta is the angle. So this is the angle theta. The angle made by the needle with respect to the x-axis. So this is the x-axis, which is parallel to the ruled lines. And this angle is theta. And this length is x. Remember that. So because this angle is theta, so therefore this angle is also theta, because we know that in the parallel lines, these two angles are same. Okay. So this was the picture. The length, so this is the part of the needle from the center to the line. Let me denote this by this green line. And because this is x and this is theta, therefore this length is x by sine theta, just by simple trigonometry. Therefore, for the needle to cross a line, L over 2, which is the half length of this needle, must exceed x over sine theta. Because if it doesn't exceed, if L over 2 is smaller than x sine theta, it will lie in between the two black horizontal lines. In other words, we have to find when we drop the needle, if I look at the center of the needle, and if this length is x, we want to find what is the probability that L over 2 is bigger than or equal to x over sine theta. Or equivalently, x is less than or equal to half L sine theta. What I have drawn here is the curve L sine theta. For this is theta and this is L sine theta. So if I look at the vector x comma theta, x, remember, is this is so if x comma theta lies in this red region, then the needle will intersect the black horizontal lines. Okay. So what we want to find, therefore, is the area of this red region and divided by the area of the rectangle, which is pi. So the area of the red region is the area underneath the curve half L sine theta for theta between 0 and pi. And that's very simple to calculate, and you will see that this is nothing but L. So the probability P that the length, so the probability P that the needle intersects the line is the area L divided by the area of this rectangle, which is L over pi. I hope this is clear to everybody. It's quite surprising. I mean, it's very difficult to just speak to a computer and hope that you will understand this. But the whole point here is that the red region is the region where if of the vector x comma theta, if the x comma theta lies in this region, then the needle will intersect one of the horizontal ruled lines which we had done earlier. And this area is L as we calculate the entire possibility, because x comma theta can be anywhere. Remember, the distance between two black lines is exactly 1. So x can be anywhere between 0 and 1, and theta can be anywhere between 0 and pi. Therefore, the total possibilities is x can be anything from 0 to 1, and theta can be anything from 0 to pi. Therefore, for the vector, it is the total possibility is this area, which is pi, the total area, and therefore the probability that the needle intersects the line is L over pi. Okay, now let's move on. So P is L over pi. In other words, pi is L over P. So now we can turn this into a question of statistics. In other words, if I drop this needle repeatedly and find out what is so we can find out we can estimate pi. We can estimate P, which is the probability. If we drop it repeatedly, we look at how often does it cross the line and how often it doesn't. So if we drop the needle 100 times and we see that only 30 times it crosses the line, then the probability is 30 over 100, which is 0.3. Okay. So in other words, so from this, we can have an estimate of P by doing this experiment repeatedly. And now, if we put in that estimate in this equation, pi equal to L over P. So L is, we know L, we estimate P, and then we can get a good estimate of pi. So this is a statistical way of getting a good estimate of pi. Actually, an amazing result is that even if the needle was bent, so it need not be a straight needle. So we were assuming that it was a straight needle like this, but it is not. Even if it's a bent needle, you'll get the same answer. And that this is a much more newer version of this. So because the Buffon's needle problem is very old, but this when it's a bent needle, we call it the Buffon's noodle problem, because the noodle, as you know, is always bent. And a good exercise for you would be to try and understand why this happens, and you can just go to Google and do a Buffon's noodle problem and try and understand what is happening. Why do we have the same result for the Buffon's noodle problem? Okay. I've been asked to give lectures of half an hour each. So this I will stop with this problem. This is called the 100 prisoners problem, and it is attributed to the Danish computer scientist Peter Bro Melterson, and it's very recent, who posed this problem in 2003. It's actually a very non-intuitive problem. So there are 100 prisoners on the death row of a prison. And suppose each of the prisoners are numbered from 1 to 100. So everybody has a T-shirt on which is given his or her number, just like our cricket players. So there's a prisoner with number 1 on his T-shirt, another with number 2, etc., up to 100. And the warden of the prison offers the prisoners a chance of pardon. In other words, if they can successfully do some problem, then they will all be pardoned, and they will get out of jail without being hung or guillotined. So what he does is that in a room, there is a cupboard with 100 drawers. The drawers are numbered 1, 2, 3, etc. And inside the drawer, the warden randomly puts one number from 1 to 100 in each of the drawers of the cupboard. So, for example, drawer number 1 could have the number 6 inside it. Drawer number 2 could have a number 12 inside it, etc. So the warden randomly puts numbers 1 to 100 in each of the 100 drawers in this cupboard. The prisoners are then told to enter the room one by one. Each one of them is allowed to open 50 drawers at a time. So the first person can go and open one drawer and another one up to a maximum of 50. And after the prisoner opens a drawer and sees the number, the drawers are closed again. Okay, so that when the next prisoner comes, the numbers are still the same. The drawers contain still the same random numbers, because that is not changed. Okay, and so the next prisoner will have the same kind of number system in these drawers. If during the search, every prisoner finds his number in one of the drawers, then all prisoners are pardoned. So in other words, if prisoner number 1 in one of the 50 drawers he opens, if he finds his number, then he comes out successful. Prisoner number 2, if he also does it, then it's successful, etc. But each and every 100 prisoners will have to be successful for the warden to pardon them. So even if only one prisoner does not find his number, then all prisoners are hung. Then all prisoners die. Okay, so each and every 100 prisoner will have to find his or her own number. Intuitively, this is actually a very small probability that they'll find a number. Why? So this is a picture taken from Wikipedia. So of prisoner number 63 opening the drawers and finding the random numbers. You know, in this drawer he finds 60, etc. Okay. So as I was telling you earlier, intuitively, each prisoner has a probability half of finding his number during the search. Why half? Because he is opening 50 out of 100 drawers. So the probability that in one of the 50 drawers which he opens, his number is there is exactly half. So the probability of all 100 of the prisoners finding their own number is 1 over 2 to the power 100, because it's half multiplied by half multiplied by half, and there are 100 of them, so 1 over 2 to the power 100, and that's an incredibly small number. So the probability, intuitively, is that the probability of them all being getting their numbers is actually very small. Okay. But the question is now, is there a strategy which will increase this probability? And indeed there is. So as I said, that the warden forgot that there was a probabilist amongst the prisoners. So this probabilist tells the prisoners to follow the following strategy. First, all the prisoners decide on a unified way of labeling the 100 drawers. So the drawers are labeled 1, 2, 3, etc. Let's say from the top left to the bottom right. Prisoner number K goes and opens the drawer labeled K first. So the first thing he does is opens a drawer labeled K. If he finds his own number there, then he comes out of the room. He's successful. Otherwise, he finds a number N1 in the drawer labeled K. He then goes and opens a drawer labeled N1. So in other words, so the random number which is there in the drawer labeled K, which we call N1, he goes and opens a drawer labeled N1. And if he finds his own number there in the drawer labeled N1, then fine. Then otherwise, he finds a number N2, then he goes and opens the drawer labeled N2. So he does this repeatedly until either he finds his own number and then he goes out, or he has opened the 50th drawer and he doesn't find his own number, in which case all of them are going to be die the next day. So this is what the probabilist tells them, the strategy. So let me repeat again. So prisoner number K goes and opens drawer number K. If he finds his own number K there, then he comes out. Otherwise, he goes and opens the number which he finds inside that drawer. If the number there is N1, he goes and opens the drawer labeled N1 and continues in this fashion. So clearly, as you may guess, that this strategy should increase the probability from what it was earlier, namely this extremely small thing. But why? So let us see. So let us see an example where there are 8 prisoners and 8 drawers, and then you can see how we can generalize to n prisoners and n drawers. Okay. So let me give you an example. So there are 8 prisoners, 8 drawers, and each prisoner can open exactly 4 drawers. Okay. So in this case, if you were to do completely randomly without any strategy, it would be, because it's a half probability of success for one prisoner, it will be 1 over 2 to the power 8. Okay. And that's also a very small number. So suppose in the random numbers which are put in the drawers are like this. In 1, 2, 3, 4, 5, 6, 7, 8, this is the labeling of the drawers. And inside the drawer 1, there is random number 4. Inside drawer 2, there's a random number 6, etc. 4, 6, 1, 3, 7, 5, 2, 8. So these are the numbers in the drawers. So what does the strategy say? The strategy says that prisoner number 1 goes to drawer number 1. And in drawer number 1, he finds a number 4. Then he goes to 4. In drawer number 4, he finds a number 3. Then he goes to 3. In drawer number 3, he finds a number 1, and then he comes out. So he's got his number and he comes out. And prisoner number 2 goes to number 2 first, and from where he's taken to number 6, from where he's taken to number 5, from where he's taken to number 7, and then he finds his own number 2 and comes out. So that's exactly the strategy. So from 2 to 6 to 5 to 7, finds his number and comes out. Prisoner number 3 goes to 3, then goes to 1, then goes to 4, finds his number and comes out. Similarly, prisoner number 4 goes to 4 and then 3 and then 1. 4 and then 3 and then 1 and finds his number, etc. So, and you can see it. So 5 also 5, 7, 2, 5. 6 goes to 6, 5, 7, 2. 7 goes to 7, 2, 5. And prisoner 8 finds his own number in number 8. So this is a successful example. In other words, each prisoner found his own number in the first 4 drawers which he opened. So this is a successful example as I write on top. Let me give an unsuccessful example. So 1, 2, 3, 4, 5, 6, 7. These are the drawer numbers. These are the random numbers inside. So prisoner number 1 goes to 1, then goes to 4, then from 4 goes to 3, from 3 goes to 8, from 8 he finds 2. In other words, in the first 4 he has not found his number. So he comes out and everybody is killed the next morning. So we'll have to understand what this strategy means and how does it improve the chances that the prisoners will survive. So as I told you, there was a successful example and there's an unsuccessful example. Let's note one thing. Okay, before we note that thing, let me introduce this notion of permutation. A permutation of the numbers 1 through n is just a mapping from 1 to n to 1 to n, which is 1, 1. So f of 1 can go to 2, f of 2 can go to 6, f of 3 can go to 8, etc. Okay. So this is a 1-to-1 mapping of the first n numbers to itself. Now, each permutation can be decomposed into disjoint cycles. That is, cycles which have no common element. For example, if I look at the successful example, remember this 4, 6, 1, 3, 7, 5, 2, 8. That's exactly, what I have here, 4, 6, 1, 3, 7, 5, 2, 8. So what is the permutation here? So f of 1 is 4, f of 2 is 6, f of 3 is 1, etc. Let me follow the strategy which I said. F of 1 is 4, f of 4 is 3, f of 3 is 1. That means we started from 1, went to 4, went to 3, and then we returned to 1. So this is called a permutation, 1, 4, 3. Okay. Similarly, if from 2 we go to 6, then from 6 we go to 5, from 5 we go to 7, and then from 7 we come back to 2. So this is another cycle. And from 8 we go to 8. So in this permutation, there are 3 cycles. The first is a cycle of length 3, the second is a cycle of length 4, and the third is a cycle of length 1. We can also draw this as a graph. So if I do 1, 2, 3, 4, 5, 6, 7, 8, so this is a cycle 1, 3, 4. So 1, 4, 3, as I showed here. 2, 6, 5, 7, that's another cycle. And 8 is just one singleton cycle. So we can draw it by these uh, diagrams. For the unsuccessful example, there are only two cycles. One is 1, 4, 3, 8, 2. This is exactly the unsuccessful example. You can go to the previous pages and see it. So 1 goes to 4, 4 to 3, 3 to 8, 8 to 2, and then 2 to 1. So this is a cycle which is of length 5, and the other cycle is of length 3. And again, we can draw the graph, which is 1 goes to 4 to 3 to 8 to 2, and then goes back to 1. And similarly, for the other one, 5 goes to 7 to 6, and then goes back to 5. So this is for the unsuccessful example. Now, there is one big difference between the unsuccessful example and the successful example. The difference is that the unsuccessful example had a cycle of length 5. And this is exactly the reason why when the prisoner number 1 went and got 4 and then 3 and then 8 and then 2, this was so 1 to 4, 4 to 3, 3 to 8. So he has opened 4 drawers and he has not found this number. Okay. So basically, so as I said, the difference between these two examples is that in the first example, all cycles are of length 4 or less. In the second example, there's a cycle of length bigger than 4. So if a prisoner gets into a cycle of length bigger than 4, then he can never find his number. Whereas if all cycles are of length 4 or less, then he always finds his number. So then, going back to the question of 100 prisoners, a similar argument will now tell me that we'll have to find whether in the random allocation of the numbers done by the prison warden, there's a cycle of length 50 or more. So I will stop now at this lecture. I want you to think about this before you start the next lecture, where I will give you a solution and say why this problem, the probability is now significantly large. Okay.